Welcome back, students, to our first video after the winter break, Solving Systems by Elimination, Chapter 6, Section 3. So I would just like you to know that I definitely reached heights of procrastination previously unknown to man, and am now making this very, very early on Monday morning. Not really. I did a lot of work. I just didn't start making videos until really late. So let's jump right in. Let's talk about elimination. Okay, in the elimination method, you're going to use the addition and subtraction properties of equality in order to eliminate a variable in a system. So that means you're actually going to be either adding or subtracting the two equations that you see, and one of the variables is going to disappear. That's what eliminate really means, make one of them disappear. Keep in mind that you're going to have several methods after we learn this to use when you're solving a system. And if you look at the system individually, you can tell which method is best to use. We're going to talk about that more at the end of the video. Okay, let's jump right in with an example. To solve a system by elimination, you're going to eliminate one variable by either adding or subtracting the two equations. So what we're going to do is we're going to take this system here, and we want to look at how we can get one of the variables to go away if we add or subtract the equations. Now, if we look at our terms, we have both equations written in standard form. So ax plus by equals c, ax plus by equals c here. And we have everything lined up. The like terms are lined up. And you should notice that because the y variable has opposite sign, same size but opposite sign coefficients, same size magnitude, but opposite signs, that means they're going to cancel out when we add the two equations straight down. So what you're going to do is add straight down. You're going to get 8x plus 5y minus 5y is going to cancel. So you can get 8x equals 8, and then you're going to solve x equals 1. So that's solving that resulting equation to find the value of one of the two variables. Now we're going to substitute that number back into one of the two equations to find the other variable. So 2 times my value for x, which is 1, plus 5y equals 17. And so I'm going to subtract 2 from each side, get 5y equals 15, and y equals 3. And that means our solution is the ordered pair 1, 3. So that's elimination, and most of you, I think, are probably going to like this better than substitution. Well, what if neither variable eliminates, though, right off the bat? So we're going to like this better than substitution, and we're probably going to like it better than graphing because it's going to turn out easier, but sometimes you're going to have to manipulate the situation. In order to eliminate x or y, its coefficients have to have that sum or difference of 0, like we just saw in that previous example. Sometimes you're going to have to multiply one or both of the equations by a constant so that when you add or subtract, the equations will eliminate. When you add or subtract the equations, that'll eliminate a variable. So let's take a look at one. All right, neither variable eliminates. Negative 2x and 21x plus 5y minus 15y. So that definitely isn't going to cut it in this circumstance. That's definitely not going to work. So first we determine which variable is easier to eliminate. So we look at the x's. We'd have to multiply the top one here. We'd have to multiply by a decimal to get it to match, so that's not very convenient. But look at this. 5 is a factor of 15. 15 is a multiple of 5. What multiple of 5? Well, it's 5 times 3. So if I take the first equation and I multiply the whole thing by 3, what does that give me? It gives me negative 6x plus 15y equals negative 96. And I'll bring my other equation and put it underneath, but I haven't done anything to change the second equation. So I multiplied that equation to get it to eliminate a variable. So in this circumstance, I only had to multiply one equation. Sometimes it'll be both. So now I'm going to proceed like I did with the other example. That's a plus sign there. So that's 15x plus 15 minus 15y's. Those are going to cancel. 15x equals negative 45. Divide by 15, x equals negative 3. Go back, plug it in, find your value for y. Ooh, got a little messy there. Let's fix that. So we are manipulating the equations in order to get the result that we want. Now, we don't always have to use whatever method we have handy. We like to use methods that are easier, that are faster, that are more efficient. All right, so this is not going to come out to a happy whole number here, negative 38, making it negative 38 fifths, which I'm going to leave, negative 38 fifths, which I'm going to leave as a fraction there, making our solution negative 3 and negative 38 fifths. So another system solved, and I didn't have to graph at all. So let's take a look at another example. Alrighty, so in this third example, we have another circumstance where it starts off where nothing will eliminate. So I can't add straight down because that would give me 7x here, and that'll give me 5y here. So that's definitely not going to work. In fact, 3 and 4 and 2 and 3, they each have the same relationship. 3 and 4 are what we call relatively prime. Relatively prime. What does that mean? Well, that means that the two numbers have the only common factor is 1. So the only common factor of those two numbers is 1. And that makes this a little bit tougher process because I can't multiply the 3 by anything to get 4, not conveniently, or the 2 by anything to get 3. So what we're going to do instead is we're going to crisscross the coefficients. We're going to multiply the entire top equation by the coefficient of the x term in the bottom equation, and the entire bottom equation by the coefficient of the x term in the top equation, and then to boot we're going to make one of them negative. So we crisscross the coefficients and make one of them negative. Now let's look at what that gives us when we multiply it out. It gives me 12x plus 8y equals 4, and it gives me negative 12x, there's the canceling part, minus 9y equals positive 6. And now I can add straight down. The x's are going to cancel. I'm going to get negative y equals 10. You can divide by negative 1, get y equals negative 10. Then you go back and you're going to plug it in. So 3x plus 2 times negative 10. So negative 10 equals 1. 3x minus 20 equals 1. Add 20 to both sides. 3x equals 21. X equals 7. And we've got our ordered pair, 7, negative 10. So elimination tends to be a little bit faster, a little bit easier to do. Let's try one with a real-world example. Yes, that's right, it's a word problem. Please try to contain your excitement. All right, the theater club sells a total of 101 tickets to its first play. A student ticket costs $1, an adult ticket costs $2.50. Say that you forgot to keep track of how many, big yawn, how many is sold of each type of ticket, but you know the total ticket sales is 164 and the total tickets sold is 101. How many student tickets are sold? So first we're going to go ahead and define a couple variables. Let's keep it simple by using x and y. So we'll make x number of student tickets and we'll make y number of adult tickets. All right. You have two different equations you can write using that setup. One is one has to do with number of tickets, and the other one has to do with the cost of the tickets. So for the number of tickets, you can say that you know the total is 101. So there's your first equation. For the cost of the tickets, you say $1 times X tickets plus $2.50 times Y tickets is equal to $164. And there's your system. So that's a nice system because actually we're going to go ahead and be able to eliminate. We're just going to take the entire first equation and multiply by negative 1. Make sure it's nice and visible there. Give me negative x minus y equals negative 101. And we'll keep the second equation the same. When you add straight down now, you cancel out the x's, giving you 1.5y is equal to 63, and then when you divide by 1.5 you get y equals 42. So I know there are 42 adult tickets. Now I have to find out the number of student tickets, and I can very quickly do that by subtracting the number of adult tickets from the total number of tickets, and I got 59. Okay, so that means 59 student tickets were sold. Good times. All right. Let's look at what happens when you don't have a single solution, but you have one of those other two circumstances we have when you have a system of equations. Alrighty, what happens when the system is consistent? So there is a solution, but it's dependent. So it's actually infinitely many solutions. Well, it's not going to look quite this perfect, but let's look at what happens with this one. Whoops, sorry about that. Let's look at what happens with this one. So I'm going to go ahead and add straight down, because if you notice, it's all set up and ready to go for elimination. The x's will cancel nicely and give us 0, but so will the y's. And so will the positive and negative 18 on the other side. So everything cancels. Now, it may not already be set up that way, but maybe you'd multiply to get it there, or what have you. But you end up with 0 equals 0, which is indeed a true statement, which indicates or points to us that in this circumstance you have infinitely many solutions. So you'll get, again, one of those true statements like we did with substitution. What about what happens when the system is inconsistent? So let's try this one. Well, this system is not quite ready for elimination. Let's multiply the whole second equation by -1. So the first equation is still negative 2x plus 5y equals 7. And the second equation is now 2x minus 5y equals negative 12. And when you add straight down, the x's and the y's will cancel, giving you 0 plus 0, which equals 0. But you get 0 equals negative 5, which indeed it does not. Indicating, because that is a false statement, that this has no solution. This system has no solution. Those two lines, indeed, if you were able to graph them, would be parallel. All right, finally, let's look at what happens when we have to start deciding which method to use. So here's 4 different systems, and yes, I'm going to give you the answers for them, so that those of you who need the practice can go through and practice, which all of you, of course, should. But the point here is actually which method makes the best sense. What's the most sensical one for me to use now that I've learned all of these different methods? Most of the time graphing, let's review what they are real quick. So our methods are graphing, substitution, and elimination. So let's think about this just for a minute. Graphing is best when the equations are already ready to graph. It's also good for use in the classroom with the TI graphing calculator. Substitution is best when one of your two equations is already solved for one of the variables, because then it's easy just to plug the other side in for that variable. And elimination is great when it's already set up for elimination, or if both equations are in standard form to begin with. So let's look at the first one. So what do you think? We've got y by itself here equals 2.5x, and then you got 2y plus 3x equals 32. Now this is not going to be a convenient one for me to solve for y, and I mean it's okay, but I'm going to end up with at least a fraction for the slope, so I don't want to do that. But I should notice that, yes, if y is by itself, then this would be a good candidate for substitution. If y equals 2.5x, let's replace that in here for y. So that would be great for substitution. And for those of you who are going to go through and do that extra practice, the solution for that one when you're done should be 4, 10. All right, how about this next one? This next one is already set up with y equals 3x minus 1 and y equals negative 1/2 x plus 4. Definitely a good candidate for, yes, I agree, that would be for graphing, because it's already y equals on both of them. And because it's a graphing example, I can see how you might want to use that graphing. Calculator wouldn't be very useful here because this ordered pair is not very pretty. It's 10/7 and 23/7. And I'll go through and double check that in just a minute just to make sure, but that's what I ended up getting for that one. So that's a toughie. So graphing may not end up being the best method there. You may have to go ahead and use substitution. On the third one, I bet you notice already, plus y minus y would cancel out nicely. So that one would be a good one for elimination. Definitely a good one for elimination. Getting those y's to cancel out. In the end, when you finish it, you would get a solution of 3/2 1, be the ordered pair, for number 3. And finally, number 4. Number 4 is not set up well for graphing or for substitution, but everything's in standard form. So elimination would be nice here. And what I would probably do is I would probably take and multiply the whole first one by 5, and the whole second one by maybe -2. And that would help you get rid of your, in that case, it would get rid of the y, it would eliminate the y. And in the end, you should end up with a solution there of negative 1, 4. So deciding which method is the best one, it's always a good idea to be conscious of what you're doing, even if it doesn't give specific directions on how to, or they won't usually give you specific directions on how to solve. You've got to decide what works best for you. All right, folks. I enjoyed making this one. I will see you in class.